Hey everyone, today we're going to look at the conservation of angular momentum. So we've said that if there is a torque acting on an object that is spinning, the torque will try to change an object's angular momentum as time goes on. So if we can say that there is no net torque, or if the internal torques cancel out to zero, what that means is that the change in momentum must equal zero, or the total momentum must remain constant. The total momentum will always remain same before and after any scenario is happening. So kind of like a linear momentum collision, we have angular momentum before with LO equaling the angular momentum after with LF. So we're going to use conservation of angular momentum to understand why the gyroscope does a couple more strange things, and we're going to look at solving problems when you want to conserve angular momentum. So the first thing here in the demonstration is if I have my arms wide. If I have my arms wide, I have a very large moment of inertia, and I have masses in my hands too to increase that moment of inertia even more. What I'm going to do is give myself a spin. So as I give myself a spin here, I have rotational motion. So I have a moment of inertia and I have an omega. Once I pull my arms in, I'm going to bring that mass close to the pivot point, which will increase my rotational motion. When I open my arms, I increase my moment and I slow down my rotational speed. Decreasing the moment increases the angular speed, and increasing the moment decreases it. So all I'm doing here is conserving momentum. I omega initial must equal I omega final. And if your moment changes from the beginning of the problem to the end of the problem, your omega will change from the beginning of the problem to the end of the problem. So now let's look at Newton's third law for rotating objects. Newton's first law says that if you are in motion, you will remain in motion. If you are spinning, you will remain spinning, unless there's an outside net torque. We see that net torques cause us to accelerate and cause our momentum to change with time. And now we've got third law. And third law before said if I punch the wall will punch me back with an equal and opposite force. So now, if one object torques at a second object, there's an equal and opposite torque on that first object by the second. So another way to say that is if I twist you, you twist me back in the opposite direction. If I torque you, you torque me back, Newton's third law. And let's show that with the wheel demonstrations here. So with our wheel here, we can follow the right-hand rule and say the momentum is pointing out of the page towards you. So due to the counterclockwise spin of that wheel, it is pointing towards you. What I'm going to attempt to do now is change the direction of the angular momentum from towards you to a different direction. So in this, I am now trying to head off and make the momentum point to the left. To make the momentum point towards the left, I must create a torque heading from you towards the left. And if I do a torque based on your right-hand rule, your thumb is the torque. Your radius is your pointer finger, and your hand that curls, or your middle fingers, are your force. So if you do your R cross F and follow where the torque is pointing, you can see that I must actually have to push up to make the wheel try and move towards the right. If my torque is to the right and my force is up, the wheel is going to torque back, and a backwards torque causes a downward force. So there's torque from me, and then there's torque from the wheel, causing the wheel to dip down. Now let's try to change the momentum. Instead of it heading towards you, I'm going to try and point the momentum to the left. In order to do that, there must be a torque to the left. And if I do a torque to the left, you can see that the wheel reacts and points upwards. So if I'm going to have the wheel point upwards, what that means is my torque to the right requires a downward force. Check your right-hand rule. So my torque to the right has a downward force. If I torque to the right, the wheel wants to maintain and keep the momentum pointing out towards you. So it's going to maintain that angular momentum in your direction, or try to. And when it does that, it's causing a torque backwards. The backwards torque is causing an upward force, and the wheel dips up. So to recap this, when I torque in one direction, the angular momentum wants to stay out of the page, and the wheel forces itself to point in opposite directions to my torque. The forces are equal and opposite to my torque. So one last revisit of Newton's third law here is that when you transfer angular momentum to something, it will transfer an equal and opposite angular momentum to yourself. So what I'm going to do here with the spinning wheel on the spinning chair is I'm going to spin the wheel, and I'm going to have the momentum pointing in one particular direction. So I've got the wheel spinning now, and when I sit on the chair, the momentum is pointing to the left. Right now, I'm sitting on the chair, momentum is pointing to the left, and no rotation is happening because I haven't tried to change the wheel's momentum. What I'm going to do now is change the momentum from pointing to the left to pointing straight down. And if the wheel has momentum downwards, I must be getting twisted in the opposite direction, so I'm getting momentum upwards, causing me to spin in the direction you see. When I flip it 180, that means the momentum is now pointing up, so I must have equal and opposite momentum downwards. And that's all I'm doing here every time I flip the wheel. The wheel has momentum in one direction, and I have momentum in the opposite direction. If I want to stop, all I do is make the wheel go back to perpendicular, and I stop my motion altogether. So all the wheel demonstration was trying to show us today was that you can conserve angular momentum, and after you have angular momentum conserved, if you cause a torque, it will torque you back and cause you to rotate to try and maintain the momentum that it used to have. So there's the link to the barrel roll that we talked about in class again. You can go back and enjoy why that actually happens. So divers and ice skaters, when they dive off the board and they start doing their flips, they have very large moments where the skater has their arms out and they have a very large moment of inertia. Their rotation is very, very slow. As they pull their arms in, or as the diver starts to tuck for their flips, they decrease their moment, they increase their angular velocity, but conserve the rotational motion they had, or momentum they had the entire time. So like in the example here that was in your reading quiz, when the kids walk towards the center here, they decrease the moment of the entire merry-go-round, and that gene gets flown off tangent to the circle because of the increase in angular velocity. So an angular momentum collision is very similar to linear collisions. Rotational collisions, if they're elastic, will have the same kinetic energy before and after. If they're inelastic rotational collisions, then energy will be lost to heat, sound, friction. So let's do a couple examples of objects that have momentum beforehand and then they have momentum afterwards. So if we look at both of these wheels here, the first wheel, I1, is spinning with an omega initial. Let's say that I1, if we do our mr squareds or 1/2 mr squareds, whatever the moment is, comes out to 5 kilograms meters squared. And let's give it a nice easy speed of 2 radians per second. So that's our initial omega. Angular momentum, I take the moment multiplied by the angular speed. So 5 times 2. If I look at the momentum of mass 2 maybe has a moment of inertia, it looks like double, so I'm going to say 10 kilograms meters squared. But the rotational motion of the wheel here at the bottom is at rest. So there is no angular momentum for wheel 2. So just like we've done in all conservation problems, angular momentum of object 1 plus angular momentum of object 2 equals the angular momentum of object 1 plus the angular momentum of object 2 in the end versus your momentum in the beginning. So the first thing I can do is say that, okay, object 1 has 10 kilograms meters squared per second units of momentum. Object 2 has no momentum since it's at rest, so I know my whole system has to have the same momentum afterwards. Well, to find the momentum of the system afterwards, I'm going to add my 2 moments because the 2 wheels now are spinning as one and solve for omega f. So my 2 moments here was a 5 kilogram meter squared and a 10 kilogram meter squared. So this is 15 kilograms meters squared. So if I want to solve for the final omega of the collision, I divide that over, and omega f will equal 0.67 radians. So the reason that the wheels slow down is because now both wheels are trying to spin as one. So all that momentum from the first spinning wheel now has to go and try spinning both wheels. So both will clamp down together and spin as one and give you this much lower speed than we had in the beginning. Let's see if this collision was elastic or inelastic. And all that's going to define that is the energies involved. Okay, so the kinetic energies of both objects, you're going to do 1/2 I omega squared. So in this case, omega is 2. 2 squared is 4, times 5 is 20. Half of 20 is 10 joules of energy. The energy for the second object, that's easy. Objects at rest, no energy. So let's look at them afterwards. Afterwards, their combined moment now is 15 kilograms meters squared. And we know that their final omega here is 0.67 radians per second. So this one can't really do in your head. Make sure you got a calculator for this. But 0.67 radians per second squared multiplied by 15 multiplied by 1/2 gives you 3.33 joules. So right there we know this is not an elastic collision. This is like when two objects hit and stuck together, which was a perfectly inelastic collision before in linear motion. Now this would be a perfectly inelastic rotational collision. So yes, we lost about almost 7 full joules of energy just by these two clamping together and spinning. Think of the frictional forces it takes from mass 1 landing on mass 2 to get mass 2 to accelerate up to their combined final speed. So there's where some of your energy is definitely going to go. So why would you ever have two spinning wheels colliding? Well, this is what happens inside your car, inside your transmission. This is a blown out view of your transmission, and you can see that if you were using, let's say, a manual or a stick shift, you have the flywheel that's spinning inside the car. When you put it into gear, that flywheel slaps against the gear and makes the gear and the flywheel spin together. Shift gears, all you're doing is picking the flywheel off one gear and slapping it onto another gear to increase the angular velocity of that gear, and that translates into the motion of the tires in your car. So let's try this example here. We have to conserve angular momentum here. This is a kid running towards that merry-go-round again, and if you think about it, there wouldn't be any angular momentum beforehand. That kid just has straight line linear momentum. But when they jump onto the merry-go-round, the merry-go-round's going to start to rotate, which means that there will be angular momentum after she collides with it. So if there is angular momentum after a collision, there must be angular momentum before a collision. So let's show how we'd set this up and prove that momentum before and after must be equal. If this is our scenario, we want to conserve momentum before and after the collision. That means that there's got to be angular momentum before, and we've got to have angular momentum after. The angular momentum before the collision here is not so straightforward, but when that person gets right to the edge of the wheel, they do have straight line momentum, and they are a radius away from the pivot point. So when they get to that pivot point, they actually have angular momentum in RMV. There's a radius, a mass, and a velocity, and they're 90 degrees apart. So R cross P will equal RMV of the person initially. Once they jump on the wheel, we can see that the wheel makes sense. The wheel is going to be moving now with I omega. But what about the person? The person's rotating too, but you could also see them as a straight line, a mass that has straight line velocity, wanting to leave the circle in a straight line, and they're still a distance away from the pivot. So really you could do RMV final for the person afterwards. And now we've set up a conservation of energy equation for before and after momentum, even though the wheel wasn't spinning before the collision. Once again, to prove if the collision here is elastic or inelastic, look at the energies. If the kinetic energies equal each other, we know they're elastic, and if those two don't equal each other, then we know it's inelastic. So look at your scenario, put in your numbers, or see if your energies are conserved or not. So once again, I'll leave you with some videos here to talk about the strange things that happen when you try to change an object's angular momentum. Helicopters are amazing when they're trying to conserve their angular momentum and how they react to the torques and the changes that you provide to them. So enjoy.